So welcome back. I wanted to do one more application of least squares, which is you'll see is not a 100% direct application. There's a little bit of tweaking that we have to do, but that's good. That's good practice for what you might have to do, practically when dealing with problems like this. But this is the application of least squares to team ranking. So one more for now. We'll actually see at least one more application of least squares. So one more least squares application. And this is team ranking. So what do I mean by team ranking? This is exactly what it sounds like. So the idea is that I have some teams playing a game of some type that is won or lost via points, so that we have a record of these games. So let's say that we have team one, team two, team three, for instance, in this example, playing a game. They're playing games against one another, so these are team versus team games, not like multi teams playing or whatever. Although there are things you could do to take account for that, regardless. But we're going to say this is team versus team here. So let's consider a few examples here, right? So we'll say case one. We'll say that team one beats team two. Team two beats team three. And we'll say that team one also beats team three. Okay. Then how to come up with a ranking here is pretty simple, right? In this case, because team one beat team two and team three. Okay, so team two lost to team one and beat team three, and team three lost to both teams one and teams two. So in this case, it's very easy to come up with a ranking, right? Team one, team two, and then team three on the bottom, right? This would be our ranking. And I don't think anyone would have an issue with this ranking. Of course, this requires that the games work out like this, which oftentimes, if you follow sports at all, know that it does not work out so cleanly. So here's another example. Let's say that we have team one beats team two, and then team two beats team three. And then team three beats team one. So now, if we're tracking the wins and losses here of the teams, right, each of the teams has one win and one loss. So team one beats team two beats team three beats team one. So team one wins against team two but loses against team two wins against team three but loses against team one, and team three wins against team one but loses against team two. So all of these teams are 1-1 if we're tracking the wins and losses. Okay, so in this case, what would the ranking look like? Right? It's not clear how this would work, right? And so, if you are thinking about, okay, these games are played for points, so maybe we need slightly more precise or more granular data than simply whether a team won or lost, right? So we need something that's not just binary, win or lose. We need to know how great was the win or how great was the loss. So we actually need to know how many points these teams won or lost by. But even then, of course, right, that might not make your situation any easier. It might actually be even more complicated to parse through how to come up with a sensible ranking in this way. So let's say that team one beats team two by 5 points. Okay, whatever those points are for this game. Team 2 beats Team 3 by 3 points, and then Team 3 beats Team 1 by 1 point. In this case, what would the ranking look like? Well, it's still maybe not immediately clear how you would come up with a sensible ranking in this way, right? And I mean, you might say, okay, we can rank the teams relative to one another in some sense, but in the end, that list, right? If you're doing this in a complete way for all of the teams, in the end, that list is going to generate like a list of numbers that you're going to be able to order, right? Hopefully in decreasing order, which is going to give you a ranking of the teams relative to each other, which is, I mean, that's what these rankings relative to each other, that's what we're looking for, right? So it's still not really clear what it is we're doing here. And so what is the idea here? So the idea first is we will track the teams. We don't need T here to indicate that they are teams. Whenever we are tracking this, we know that the numbers involved refer to a team. So we can just track the teams like by the indices. So team I, we can just track that with the index I. And team J, we can track with the index J. Right, so when we have an index floating around, it refers to the team in question corresponding to it. And so let's say that the ranking of team I call that R sub I. So that the ranking of team J would be R sub J. Okay. And so in this way, the main idea is that if Team I and Team J play, so if Team I beats Team J by P points, then the thing that we are imposing here is that the difference in their rankings like this is P. So the number of points that I win by is merely the difference in the rankings. This intuitively, this seems like a really nice idea, a really nice way of encapsulating it, right? Because and you might say for a second, right? Well, in the season, what if the teams play each other more than once? And we'll talk about that. But just for now, thinking in your head, you say you have a list of teams, and they just each play each other once, right? Then the rankings, right? Their individual rankings under this. The difference between those rankings is the number of points that the winning team won by. Now, whenever you're setting up problems like this, you have to be careful that the language you're using, in this case English, is not like getting in the way of what you're of what it is you're trying to describe. So the notion of winning, right? Like that's almost like a meaning we're assigning to the thing. You can talk about winning by negative points, for instance, right? And you would in English you'd refer to that as losing. But in the context of a linear algebra problem, there's no distinction apart from the sign, right? So that's something that we're about to see here in a second when I do this. So for instance, right, to show this is really the thing that lets us set up the equations that we're going to ultimately use. We'll see later that when we get to the end of this process, there's some shortcuts that we don't necessarily need to go through the hassle of setting all this up. But in order to see how that works, we really have to set it up like this at least once. So that's the idea. All right, so real quick, So for instance, if say Team I beats Team J by 3 points, this would translate as the equation R sub I minus R sub J is equal to 3. Okay. Now, the quick question, how does this work? For losses and ties. Now, a couple things you could say. You could say, well, every loss for one team is a win for the other team, so you could just rewrite it differently. But for algebra reasons, we like to keep like a consistent ordering, convention on one side that makes our life easier when we go to set up this matrix equation. And so recasting everything as winning is nice and preferable in a way. What do I mean by that? Well, we'll see when I write out the examples here. But how about, so for losses, how can I think about this? So if Team I beats Team J by 5 points, this would be R sub I minus R sub J is equal to 5. Okay. If, say, Team J beats Team I by 5 points, you would write this as R sub J minus R sub I is equal to 5. But notice that I could write this in another way as R sub I minus R sub J is equal to minus 5. So that this is the same as saying Team I beats Team J by minus 5 points. I.e., Team I loses to Team J by 5 points. Okay. So this is what I meant earlier. So notice that, a reason that I might want to do this instead of always talking about like wins here, like, here I swapped this, is when I'm setting up the matrix equation, right, it is convenient for me to have the same convention always. So for always to have R sub I minus R sub J, ordered in this way. Like you'll see what I'm talking about when we start writing out the system of equations, but being able to recast losses as negative wins in this sense, right? Wins by negative amounts of points is important because it makes this setup that I'm doing easier. It makes it more straightforward to do this. All right, so Team I beats Team J by minus 5 points is the same as Team I losing to Team J by 5 points. So losses are taken care of here without even having to change the order, right? Just by a loss is just a win by negative points, right? That's a way to be optimistic. What about ties? So in the event of a tie, if Team I and Team J tie, and you might say, well, just play a sport that doesn't allow ties. But like a lot of sports that you don't even consider still actually allow ties technically under their rules, even if they're rarer in some than others. So ties are technically something you got to take into account because they happen in many sports. Right, from boxing to American football to everything, they can still a draw can still happen. So you have to take account for those. So then what does a tie look like? It looks like both teams winning or losing by 0 points, right? So what it looks like is this. Now you might rewrite that immediately as R sub I is equal to R sub j. Now think about it. If you have two teams that play each other only once and they tie that one time they play each other, then considering their rankings equal makes perfect sense, right? I mean, if you have two teams, they play each other once, they tie when they play each other, shouldn't their rankings relative to each other be the same, right? Shouldn't their rankings be the same? That makes sense intuitively, right? Now you might say, well, you know, if there's other teams involved and one of the teams does a lot better against the field than the other team, then that team should be ranked higher, and they will be. Okay, but if like this is the only information we have, their two rankings being the same here, at least makes sense for this equation. Okay. Okay. So how do I want to do this? How do I want to treat this? So knowing this, I want to now set up an example and ask about a ranking of some teams. So here's a big example that we'll do that we'll spend a good amount of time on. Okay, so let's say we have 4 teams. Okay, so team 1, 2, 3, and 4. Okay, we are going to notice that here's the record of games played. Where winning by a negative point value indicates a loss, but I'll indicate that also when I'm actually writing it out. Okay, so I got 4 teams, T1, T2, T3, and T4. Not too creative with team names. Okay. So then what is my list? So the first on the list, T1 plays team 2 and wins by 2. And next, team 1 plays team 2 again and wins by 1. And then we'll say team 1 plays team 4 and wins by -2, which of course means loses by 2. And then team 2 plays team 3 and wins by 1. Team 2 plays team 4 and wins by 3. And then team 3 plays team 4 and wins by -3. That is, loses by 3. Now you might say that some teams play more games than other teams, and that's true. But this happens in reality, right? This happens, college football. It can happen, and it has happened in the past more than once that a team ends up playing one less game, but either because their conference doesn't have a conference championship game, or they don't make it to the conference championship game, but they qualify, for playoffs or for a national championship anyway. Like that has occurred. So they end up playing less games, but end up ranked higher as a result. And you can talk about the fairness or unfairness of these things, but that's why we're discussing rankings in the first place, right? It's a non-trivial problem to come up with a ranking that is in some way like as objectively accurate as possible. So anyway, so this is our list here. Okay, and so what does this translate to? Let's write out the equations this translates to. Team 1 plays team 2 and wins by 2. That is the equation r sub 1 minus r sub 2 is equal to 2. Team 1 plays Team 2 again and wins by 1. That is the equation r sub 1 minus r sub 2 is equal to 1. Now you see that repeated teams playing each other more than once, which of course happens very frequently in sports, right? Sometimes it is mandated that this happens, depending on the sport, depending on how it works. So in some like English Premier League soccer, right? I think I think every team has a home and away game in a league. Maybe there's like 20 total teams, so 19 others, so like 38 total. So you play 19 games twice. So yeah, 38, something like that. I think I haven't followed that in a while, but I think it's something like that. So in that case, every team plays each other exactly twice in a season. Team 1 plays Team 4 and wins by -2. This is so now we're seeing the benefit here in terms of organizing these equations. So because I can rewrite it in the same order here, this is r sub 1 minus r sub 4 is equal to -2, so that I do not have to even change the order here. Here, Team 2 plays Team 3 and wins by 1. So this would be r sub 2 minus r sub 3 is equal to 1. Team 2 plays Team 4 and wins by 3. This is r sub 2 minus r sub 4 is equal to 3. And then lastly, Team 3 plays Team 4 and wins by -3. This is r sub 3 minus r sub 4 is equal to -3. And so here is my system of equations. So that if I were to try to solve this, what would it look like? I'm just going to write this out now. So I have 4 teams, right? I have 4 teams. Writing this out as a matrix equation means that I have the following matrix. So I have R1, R2, R3, and R4, right? That's what the columns indicate here. So then what does this look like? This would be 1, -1, 0, 0. 1 -1, 0, 0, the exact same copy because it's the same equation. So the only difference between these two is the right-hand side, which will be on the other side. Next, I have 1, 0, 0, -1. So you very quickly come to see that all of these rows are going to have a 1 and a -1 here, right? And that's just the nature of how we've set this up. So because it's one team versus one team, right? And because we were setting up these rankings such that the difference of the rankings is equal to the point value of the win. That's how this is going to be, right? It's r sub I minus r sub j is equal to p, right? In each case. Okay, so the next one is 0, 1, -1, 0. The next one is 0, 1, 0, -1. And the next one is 0, 0, 1, -1. So that is my matrix, my coefficient matrix of these left-hand sides of these equations. That is, of course, multiplying the unknown vector r1, r2, r3, r4. And that is equal to the vector containing all of the point values. So this would be 2, 1, -2, 1, 3, -3. Now, the thing, of course, that you notice immediately here is that this thing doesn't have a solution, right? So you're not too shocked or surprised that this thing doesn't have a solution, but it definitely has no solution. Well, not to beat a dead horse here, but of course, in the past few days, every time we have encountered a matrix equation like this that has no solution, what is it that we do? Well, let's try least squares. Okay, so let's try least squares and see how this helps. So here's the thing I'm trying to solve. It has no solution. I'm going to try least squares to solve this. So let's do that. So when we apply least squares, what does this look like? So we're writing out, we'll call it, so our normal equations look like this, A transpose A. The vector, we're finding a vector of ranking, so I'll call that vector R, is equal to A transpose times the vector containing the point value, so I'll call that vector P. So this is what I'm looking at here. Now, of course, you might, instead of R bar here, you might write R hat to indicate that we're finding the least square solution, whatever. Okay, maybe I'll do that. Just stay consistent in case you're looking at the notes. So what does this look like? I'm going to write this very long thing. The transpose of A is 1, 1, 1, 0, 0, 0, minus 1, minus 1, 0, 1, 1, 0, 0, 0, 0, minus 1, 0, 1, and 0, 0, minus 1, 0, minus 1, minus 1. So there's my transpose times my matrix A that I just copied down, which is 1, minus 1, 0, 0, 1, minus 1, 0, 0, 1, 0, 0, minus 1, 0, 1, minus 1, 0, 0, 1, 0, minus 1, and 0, 0, 1, minus 1. There it is, times this vector R hat that I'm trying to solve here, my least square solution thing, is equal to that thing. I'm not going to rewrite it, so this is my A transpose. This is A. Just to keep it on one sheet, I'm not going to rewrite it. A transpose times my vector P, which is the vector of point values. There it is. Okay, which, when all is said and done, when I actually multiply this out, gives the normal equations as 3 minus 2, 0, minus 1, minus 2, 4, minus 1, minus 1, 0, minus 1, 2, minus 1, minus 1, minus 1, minus 1, 3. Times R hat is equal to my the result of multiplying this A transpose with my vector point values, which is 1, 1, minus 4, 2. So this is the thing that I get. I'm going to call this new expression M times the vector R hat is equal to Q. This is what I'm going to call this. So here is my M and here is my Q. Okay. Now, the question, before I solve this, what do I know about M? Now, some of these properties that I'm talking about with M, we already knew even in other contexts because some of them come just directly from how the normal equations are written. So, I'm going to ask you the same question I asked in yesterday's lecture, which is, do you notice anything about this matrix M? Any sort of property that it has? If you do, you can let me know in the chat. It's the hint is that it's the same property that I mentioned in yesterday's lecture that we get as a result of this these normal equations involving A transpose A. So that's why we get this thing. Okay, well, if no one notices it, then what I will say is it's symmetric. So notice that across this main diagonal, it's the same entries here. Right? What's on the diagonal doesn't matter for a symmetric matrix. The only thing that matters is what's off of it. And the point is that M transpose is equal to M. But there's actually a lot more than that. That's just one thing. The fact that M is symmetric is actually going to be true in any of these normal equations problems because this M ultimately is A transpose A, and A transpose A is always symmetric because of how the transpose works. So that is the deal. That M is going to be symmetric. There's a lot more we can say. So in fact, here's what we know. So first of all, we have our matrix M. We have the equation MR is equal to Q. I think I used hat here. Doesn't matter. And let's say that in our case, we of course had like a list of 4 teams and we had their records, but we can make some generalizations here just based on how this works. You can see that it doesn't matter the number of teams or their record. This is going to work out the same. So let's say that there are T teams. So T is the number of teams, and G games were played. Then what do you notice about the matrix M? So facts about M. Well, M, so first fact about M. M is a T by T matrix. Let's check to make sure that this makes sense. So this M that we got in our example is a 4 by 4. There were 4 teams. But is that just a coincidence? Well, no, because where does this come from? Let's look at what happens here, right? The matrix A that we started with has 4 columns because there were 4 teams, right? So setting up this original equation, there are 4 columns because there's 4 teams. So that's why A has 4 columns. Because A has 4 columns, A transpose has 4 rows because that's how transpose works. And when you multiply A transpose A, you have a 4 by 6 matrix multiplying a 6 by 4 matrix, which gives you a 4 by 4 matrix. Now, in this case, it's 4 by 4. But the point is that in setting this up, A is going to have the number of columns equal to the number of teams, which means that A transpose is going to have the number of rows equal to the number of teams. So A transpose A is going to be T by T, which that's just M. So M is T by T. And this doesn't matter that we are in this special case. You can see exactly where that comes from here. Okay. And someone mentioned in chat, diagonal entries correspond to the number of games team plays. The IJ corresponds to games between I and J. Yep, that's right. That's exactly what I'm about to say next, which is that this matrix M actually encodes a lot of info about the games that were played. In fact, it encodes so much info that we're going to see ways of skipping the process of setting this up entirely and just writing M directly from the record of games that we have. Okay, but the first way to see that is second fact. The diagonal entries. Makes sense to talk about diagonal entries now since this is a square matrix. The diagonal entries, we'll call them M sub T, corresponding to the team, equals the number of games that team T played. So let's see that this makes sense before I move on. Well, m sub 1, 1 is 3. Maybe I'll just write it here. Right? M sub 1, 1 is 3. M sub 2, 2 is 4. M sub 3, 3 is 2. And M sub 4, 4 is 3. So if this pattern holds, it should mean that Team 1 played 3 games, Team 2 played 4 games, Team 3 played 2 games, and Team 4 played 3 games. So let's see that this is the case. Team 1 plays exactly 3 games. Team 2 supposedly plays 4 games. So they play Team 1 twice, and then Team 2 plays Team 3, and Team 2 plays Team 4. So Team 2 plays 4 games. Team 3 plays Team 2 once and Team 4 once, so 2 games. Team 4 plays Team 1, Team 2, and Team 3, 3 games. So that is, in fact, how that works. Now, why does this work? Okay, why does it work out like this? These diagonal entries tell you exactly the number of games the teams played. Well, if we actually write out what this is in terms of, we know, right, that M is A transpose A. And the thing about the matrix A is this is a very simple matrix, right? So notice, first of all, and I'll write all this down later as well, that the sum of each of the rows of A is actually 0 because each of them has a 1 and a minus 1. Right? So the sum of each of the rows individually is 0. Another thing to notice, though, is that choose any column you want to in A. That column is the negation of the sum of the rest of the columns, which, and I'll write that out here in a second. You can just notice it. We'll look at the first column, right? So the first column, 1, 1, 1, 0, 0, 0. If I sum the 3 remaining columns, what do I get? I get minus 1, minus 1, minus 1, 0, 0, 0. And minus 1, minus 1, minus 1 is the negation of 1, 1, 1. So the point is that these columns are not linearly independent. Now, you already know what that means for the least squares solution, right? When A is not invertible, that is when its columns are not linearly independent, what that means is that the resulting least squares solutions equations, the normal equations, have infinitely many solutions. So we'll talk about what that means in our context here in a second. But the point here is that this A, we already know its columns are not linearly independent. Okay, but M is A transpose A, and I can actually work out exactly what this means for the diagonal entries. Means this diagonal entry is a sum of the following, right? It's a sum of the entry of A transpose in the tth row and first column times the entry of A in the first row tth column, plus the entry of A transpose in the tth row second column times the entry of A in the second row tth column, and so on. I mean, this is just from my definition of matrix multiplication, how matrix multiplication works, plus the entry in A transpose in the tth row gth column times the entry of A in the gth row tth column. Okay, which is this would be A1t squared, since this is A transpose here, right? Plus A2t squared, and so on, plus A gt squared. And even like this alone isn't enough without knowing what these things are, but we know exactly what these things actually have to be, right? So, and for any little g that is between 1 and big G, remember big G is the total number of games played here, we know that A sub gt is plus or minus 1 if and only if in game G team T is involved or team T played. Okay. Otherwise, you get 0. And so, what does this mean? It means that I'm squaring this, so I get a 1 for every game Team T was involved in, right? So what this does is it counts, right? There is a 1 for each one of these entries corresponding to a game. If we've listed all the games from game 1 to game big G, right? I get a 1 every time Team T was involved in that game and a 0 otherwise. So then I'm just counting the number of games that Team T was involved in. So this is why, right? This is the explanation for why. Okay, this works the way that it does. All right, now, as someone pointed out, we can say a similar thing, right? We can say a similar thing on the off-diagonal entries. So even if we're talking about the off-diagonal entries, so for instance, if S is not equal to T, then the entry M sub st is equal to the negative of the number of games S and T played. Okay, so how does this work? Let's look at M here. So for instance, we have, let's look at this entry. This is M sub 1, 2, which should be, since it is minus 2, what does that mean? According to this, it should be the negative of the number of games S and T played together is what I mean here. And here I have teams 1 and 2. How many times did they play each other? Twice. Teams 1 and 2 played each other twice. So this is minus 2 because it's minus the number of games they played with each other. Okay, what about this entry that's 0? So this would be M sub 1, 3. So of course, notice that I could have said this is symmetric, so I don't even need to do this. You already know that they equal. But now you see why, intuitively, again, here's another reason for why this is symmetric, even if you knew nothing else about the fact that M is A transpose A. The reason that these have to be symmetric is, listen to the way I phrase it in words. It's minus the number of games teams S and T played. But that's no different than minus the number of games teams T and S played, right? I could have flipped those and it wouldn't have had any difference, like in terms of language. This tells us that these two things have to be the same, and they are. This is symmetric. M sub 1, 3 is 0, which should tell me that the number of times that teams 1 and 3 played is 0. And in fact, when we look, team 1 did not play team 3, right? Team 3 did not play team 1. So the number of times teams 1 and 3 played is 0. So that makes sense. All of these other entries are minus 1 because each of the other teams played each other only once. So team 1 played team 4 once, team 2 played team 3 once, team 2 played team 4 once, and team 3 played team 4 once. So all of these are minus 1. Okay. Now, why does that work? Well, for a similar reason, right? What is the why? So similarly, M is A transpose A, and so I can actually just write out generically what M sub st has to be. It is A transpose, the S1 entry of A transpose times A1t, plus, and so on, all the way out to the SG entry of A transpose times the GT entry of A, which when I write all of this out, this is A1S times A1T plus and so on, all the way out to AGS times AGT. But the thing about multiplying these, what are these products here? AGS and AGT is equal to -1 if and only if in game G both teams S and T are involved. So, if in your game G either S or T is not involved, this is 0. And so you get a -1 every time both S and T are involved, so then you get minus the number of games they played together. Okay, you get a -1 for each time they play together, otherwise you get a 0. Okay, so what this counts is it's minus the number of games they played against each other. Okay. So you can let me know if there's questions about that in the chat, but that's how this goes. So yes, someone posted this fact in the chat that it tracks, either you said that it tracks the number, minus the number, however you said it. But yeah, this is minus the number of games they played against each other. Okay, more facts about M. We're not done. So these are 3 facts about M. What's another fact? Thing that we noticed even yesterday in lecture, M is symmetric, which means that M transpose is equal to M. Again, this is actually baked in from the fact that M is A transpose A from the normal equations. This is always going to be symmetric because of that. Okay, what's another fact? So I have 2 more things to say about M, and these 2 things are important, especially for going forward, like how to deal with some of this stuff practically. So the first thing is any single row of M can be calculated from the other rows And why is that? Well, if I eliminate a row of M, but I keep all the other rows, I can reconstruct that row that I deleted from the fact that the other rows still give me a complete game history. Because I know the records of against all the other teams, so I can reconstruct that first row from all the other rows just because I have all of the info already. Okay, so this is since any team's game history can be determined from knowing all other teams' game histories. Okay. Note also that each row is the negation of the sum of the other rows. This was actually a property that A's columns had, right? Okay. Now you could say, wait, then okay, I can reconstruct any single team's game history from knowing all other teams' game histories, but what if I don't perfectly know all other teams' game histories? Well, then I I can't reconstruct row 1, or not necessarily row 1, but I can't reconstruct the row that I've deleted in that case, because I am now missing too much data, and I don't know for sure how to reconstruct that missing row. So I can't do this for 2 rows. So right, any 2 or more, but this is true even for 2. Any 2 rows of M cannot be calculated from the remaining rows because it is impossible to know how those 2 teams performed without knowing something about at least one of them. Right? So I can't know what happened, but like if I am missing, say, the rows corresponding to team 1 and team 2, right? Uh, and again, you don't have to think of the rows necessarily as corresponding to a team, but they do, right? The diagonal entry tracks how many games total a team played, and the off diagonal entries, tell you about game histories with other teams. But if I'm missing 2, then I now am missing too much data to accurately reconstruct everything, because now I don't know how many times those 2 teams, for instance, played each other. Right? So now I can no longer construct that matrix. And so this is telling you more than this, though. So these 2 combine to tell you the following, which is the rows are linearly dependent. But if I remove a row, the remaining rows are linearly independent. So the matrix as it is, the rows are linearly dependent. But if I remove one of these rows, the remaining rows are actually linearly independent. So you can think of this as like being barely linearly dependent, if you like. It's that I know that if I remove any single row, the remaining rows are linearly independent. So that's nice. At least this is what 5 and 6 combine to tell you in terms of linear dependence or independence. Okay. Now, what do I notice about the other things in my equation? So note in Q, this vector Q, any entry is the negative of the sum of the remaining entries. Okay. Let's go back and see. So, for instance, here's my Q. So let's look at 1. Is 1 the negative of the sum of the remaining entries? So the sum of the remaining entries is 1 plus minus 4 plus 2, which is minus 1, and 1 is in fact minus minus 1. Minus 4, the remaining entries are 1, 1, 2. Summing that, I get 4. Minus 4 is in fact minus 4. But why does that work? Right? Why is that a thing that happens? What happens if I sum up the total points won and lost among teams? What is that? If I consider the total points won by or lost by among teams in this the way that I have this set up, what is this? Well, any if one team won by 4, the other team won by -4, right? Or lost by 4, right? But it's easier to see when you just talk about winning here. So any team winning by 1 means the other team won by -1. So the total number of points won and lost are 0, right? It's truly a zero-sum game in this sense. So that the total number of points here is 0. So of course the sum of the remaining terms minus that is any particular entry in this vector Q. Okay. Now, we already saw what I'm about to say next, which is all the way back in our matrix A, when we first wrote this out, I noticed that the columns are not linearly independent because it's easy to see in this case because everything is 1s and -1s. So you could see, for instance, that column 1 is minus the sum of columns 2, 3, and 4 here, for instance. Okay, but even when we get to this point and we get that the rows of M are linearly dependent, now we know it from this angle as well. All of this is combining to tell us that this equation that we have ended with, which I'll flash again here, this thing, has infinitely many solutions. I do not get a unique least square solution. So our equation, M r hat is equal to Q, has infinitely many solutions. We knew it had to have at least one solution because it is in fact a least squared, it's a least squares problem, which always has to have at least one solution. But now we're in this case where it has infinitely many solutions, right? So previously in all the other examples we did, we had an invertible A transpose A. And remember, I mentioned back then multiple times that what happens, or when that happens, is exactly when A itself is invertible or the columns of A are linearly independent. Okay, so here we explicitly have that the columns of A are not linearly independent; they are linearly dependent. So we are in the case that this has infinitely many solutions. Now, sometimes, as I mentioned, when you are talking about a least square solution, having infinitely many solutions is not necessarily a bad thing. You're looking for a closest possible solution in some sense. And so since you're looking for a closest possible solution, having infinitely many that are the same closeness is not necessarily bad, but it is in fact inherently bad for us, because what would this even correspond to, right? We are trying to find a ranking. Right, we're trying to find a ranking, and I'm going to talk in a second intuitively about what it means, like what a solution even means in this case. But we're going to try to find a ranking, and so we would not be happy that there are infinitely many such rankings that are just as good, quote, as the one that we list. Right, that kind of maybe defeats the purpose of a ranking, right? We want there to be just one. So then how do we fix this? So the first thing that maybe I should say is what is it that we are even finding in least squares, right? So first, what would a least square solution in this context even mean? Well, it means, so if this is my question, then my answer is that it means finding the team rank values such that if the teams had these rankings and played the games they did, those game outcomes as a vector would be as close as possible to the actual game outcomes. Now, this actually sounds great, right? This kind of sounds like a dream scenario in terms of what a ranking should mean, right? Because in theory, this is telling you that like if you have this ranking assigned, from this ranking, you can do a prediction on like what each of the teams playing each other, what those game outcomes would look like, right? Which is much better than simply say a list like AP top 25, right? In college football or something. This is a ranking that purports to tell you exactly what the game outcomes would be if you have this set up. So this sounds great. So this sounds like exactly what we want. So we want to do this. Now, the problem is in our case, we don't like having infinitely many least square solutions because we want one ranking that does this. We do not want a choice in the matter here. So how do I fix this? So how do I fix this? So what we are going to do is called Massey's method, which is a quick fix for this thing not having a unique solution. The way of correcting it is essentially deleting one of the rows, which we know can be reconstructed from the other rows anyway, but deleting one of the rows and imposing in its place, replacing it with a row that corresponds to, we'll say, a reasonable assumption on these rankings. Okay, so what do I do here? Let's start on the next page here. So the idea is to modify M and Q. So we have the following equation, MRQ. I want to modify M and Q. Now, for simplicity of notation, I'm not going to come up with new notation to indicate this modified M and Q. I'm just going to modify it and then keep going to solve, but this is what we do. So how do I do this? So what does this modify M mean, and what does modify Q mean? So for modifying M, we replace the last row with all ones. And here we replace the last entry of Q with a 0. What does that correspond to? So this corresponds to the condition which is simply that the sum of the rankings for all of the teams is equal to 0. which, you could say, well, does this make sense? Well, making sense is kind of relative here. The main thing is that it adds a requirement that is going to impact the numbers that we get for the ranking, but the relative rankings are going to be unchanged. So what this means is that some teams are going to have negative rankings as a result of this. But I mean, negative numbers, we know how ordering works, right? We know how the order of real numbers works. We know that positive numbers are bigger than negative numbers, and we know that what the difference between a smaller negative number and a more negative number is, right? Or a less negative number. We understand how order works on the real line. So this isn't going to impact us. So that's what happens. So I'm just gonna call the new matrix we get M and the new vector we get Q, and I'm not gonna put like a tilde over them or anything. Sometimes you'll see something like this to indicate they've been changed. That's fine, but I'm not gonna do that. So the other thing to note is that this row R sub t, if I consider it as a row vector, do I want to write it like that? I don't want to confuse you. Let's write it like this. So row t dotted with row I, if I is 1, 2, anything up to t minus 1, this is 0. Okay. This is 0. How do I know that? Let's go back to, actually, I'm gonna go ahead and write it out, and then we'll see how this is. So let me remind you what our equation was. It was this thing. So I'm going to rewrite this now in my modified form. So I'm going to replace the last row of M gets replaced with 1, so the last entry of Q gets replaced with a 0. So rewriting this, reading row-wise here, 3 minus 2, 0 minus 1, minus 2, 4 minus 1, minus 1, 0 minus 1, 2 minus 1, 1, 1, 1, 1 times this vector r hat is equal to my vector q, except I've replaced the last entry with a 0. So this is 1, 1 minus 4, 0. So this is my modified m and my modified q. Now it makes it easier to see this thing that I'm claiming. I claim that this row that I've replaced with all ones, when I dot it with any other row, I get 0. You can check in this example that is exactly the case, because dotting any of these rows with 1, 1, 1, 1 just means summing the rows. And we've already talked about how the sum of each of the rows is 0. Okay, and the reason why is those previous facts about M that we mentioned, right? This is the total number of games that Team 1 played, which is 3. And then this is minus the number of games Team 1 played against Team 2. Minus the number of games Team 1 played against Team 3, which is 0 in this case. Minus the number of games that Team 1 played against Team 4. So summing the row, obviously, because these, in everything that's off the diagonal, I have a minus here. This is going to be minus the total number of rows, or sorry, total number of games that Team 1 played, plus the number of games Team 1 played. So that's it. So all these are going to be 0. So this is what I get, which means that row T is perpendicular or orthogonal to all other rows. What is the purpose of noticing that? This is a quick way of noticing that it is not a linear combination of them. Right? Okay, here. And so this is the thing that tells me that, now this is invertible. Okay. So this new matrix is invertible because the remaining rows we already knew was linearly independent if you deleted any row, right? So remember this fact about M that we mentioned, which said that if you remove a single row of M, the remaining rows will be linearly independent. They are, and the row that you have added is not a linear combination of the other. So automatically, always, if you follow this process, the matrix you get is linearly or has linearly independent rows, for instance. So it is an invertible matrix in this way, and so now we have a unique solution. So now we have a unique solution. In this example, let's see what this unique solution is. So in this case, so let's just bring it back on in case you're following along here. So here, I invert this, and my vector r hat is just the inverse of this times this vector. So that r hat is the vector. I'm going to write them as fractions and then decimals. So this would be 1926 in the first slot, 926 in the second slot, minus 41 26th in the third slot, and 1/2. Which, don't worry if that's a little ugly looking. Written as decimals, this would be 0.730769, 0.346154, minus 1.57692, and lastly 0.5. What does this say? So this contains the rankings of team 1, 2, 3, and 4, right? So rewriting this, this is R1, R2, R3, and R4. But it makes sense now to give our ranking in descending order. So our ranking okay, team 1 has ranking 0.730761 or 769. That's the largest of these numbers. Team 4 comes next. Team 4 has ranking 0.5. Then team 2 0.346154. And team 3 has the lowest ranking, which is minus 1.57692. So that our ranking, if we're assigning numbers, is 1, 2, 3, and 4. So team 1 is ranked first, team 4 is ranked second, team 2 is ranked third, and team 3 is ranked fourth. The question is, does this mesh with the actual example? Does this make intuitive sense if we're looking at this? So let's go back to the very original problem statement to see that this actually makes sense for this example, because we've been doing the same example the whole time essentially, although we were able to see a lot about the general question here, or the general process. So does this make sense? Let's see. Team 1 against team 2, 1 against team 2 again, and lost to team 4. Okay. So their record was 2-1, but of course they played the same team twice. Team 2 won against team 3, and team 2 also won against team 4. So they won twice and did not lose, so they're 2-0. Team 3 wins against team 4 by -3, which means they lose against team 4, and they also lost uh, uh, against Team 2 here, right? So Team 3 lost against Team 2 as well. So Team 3 is 0 and 2, right? Team 4 played 3 times and was 2 and 1. Okay, so Team 1 is 2 and 1. Team 2 is 2 and 0. Is that right? No, Team 2 is 2 and 2. Sorry. Trying to keep track of all this in my head, doing a terrible job. So Team 1 is Team 1 is 2 and 1. Team 2 is 2 and 2. Team 3 is 0 and 2, and Team 4 is Team 4 played also 3 times and won once. No, they won twice, so they're also 2 and 1. Okay. So I think that works here. Okay, so these are my records, right? Now, just looking at these records, of course, Team 2 has 2 losses, but Team 2 beat Team 4, which has 2 wins, and also beat Team 3. Team 3 didn't have any wins. Team 1 played Team 2 twice, but won both times, and Team 2 had 2 good wins. So the question is, does this make sense? But Team 1 had a 2 and 1 record. Team 4 also had a 2 and 1 record. The 2 wins, though, that Team 1 had were against Team 2, which had 2 other good wins, even though they had 2 losses. Team 3 had no wins. So looking at these rankings and trying to make sense of them, you say, okay, according to these rankings, in relative terms, these numbers are pretty close. So according to this ranking, even though we have a hierarchy here, so we do have a ranking. None of these are tied, but these are fairly close. So this ranking would say that teams 1, 2, and 4 are actually pretty close to each other. Team 3 is like significantly further down, and you can see that, well, that kind of makes sense because Team 3 had 0 wins, right? They lost the only 2 games they played. So in terms of whether or not this ranking makes sense, well, it seems like at least that it's not too far off what is actually going on. Okay, so the question is, does this seem like a reasonable ranking based on those records and looking at this, treating it like, your favorite sport? And the answer is, it seems like it's fine, more or less. So anyway, that is all we have time for today. I will finish up. It won't take me that long. It'll take me maybe like 15 minutes in Monday's lecture to finish up this business on team ranking, but you've at least seen how to do all this team ranking stuff, which means it's fair game for any homework that I post soon. So I'll be posting your homework soon, either later today or maybe over the weekend, sometime Saturday, and it will be due next week. We'll say it'll be due by probably Tuesday, 11:59 p.m. So be looking out for that. If I don't post it till later, then it'll be due maybe one day later. It might be due on like Wednesday or something, but I will let you know. So just be on the lookout in the next day or two for me to post the homework. When I do, I will make an Elms announcement, so you don't have to be, constantly looking or whatever. You will get an Elms announcement ping when the homework is posted. So that's that, and have a good weekend, and I will see you all on Monday for more of this stuff.